Okay, I'll get started. Hope you can all hear me okay. Um, so I'm going to just work through the practice test. As mentioned, the practice test has the format of the real test. So it has the multiple choice, it has the numerical answer questions, and it has the long, fully worked out problem. It has the same point assignments as the real test, same number of questions as the real test, is covering the same material, same content, same chapters and sections as the real test. But of course, the it doesn't have the real test problems are different from the practice test problems. This will work best probably if you interrupt me as I'm working through this. If you have questions, so you can interrupt me by just speaking, or you can put it in chat. I might not see it as quickly in chat because I'm not well trained in looking at chat, but either way is fine with me. Anyway, I'll go ahead and get started. So question number 1 on the practice test. So this question says that we've got a box of mass m, and it's poured across a rough horizontal floor at constant speed. And we've got to answer some questions about the work done by the normal force on the box and the work done by the friction force on the box. And so we're going to try and answer those questions. The way I would normally start this is, kind of with a sketch. And I would add to the sketch the various forces that are acting on the box as it's slid across the floor. So one force is the force of gravity. We're very familiar with that. A second force is the normal force that counteracts gravity. We're familiar with that. There's the person who's pulling the box. The person's exerting a force. I'll just call that F. And then finally, it's a box on a rough surface, so there's a frictional force. And I'll call that F subscript F. And so those are the forces. And the question asks us really about the work done by the friction force and the work done by the normal force. That's wrong. This should be weight. So the next thing I did was to think about that equation for the work done by a force. And here's that equation. And you can apply this to any force and calculate any work done by any force. So W is the work done, the joules of energy that are transferred, and F here is the magnitude of the force that's acting, X is the magnitude of the displacement, and the cosine of this angle theta, that theta is the angle between the direction of the force and the direction of the displacement. Okay, so with that, we can set about answering these questions about the friction force work done and the normal force work done. Work done by normal force. Well, the key thing here is that the normal force, is you look, is at right angles, 90 degrees to the motion. So the angle between the direction of the force and the direction of the motion, that's 90 degrees. And cosine of 90 degrees is 0. So the work done by the normal force is 0. Work done by the friction force. Well, if you look again, look at the picture. If you look at the work done by the friction force, it's acting opposite the direction of motion.
This is office hours. He's going over the practice test.
So it's acting opposite the direction of motion.
Yeah.
Let me, so I'm hearing everybody else right now, so I'll mute. And then if you want to ask a question, you can just unmute yourself. So the work done by the friction force, the key thing is that the friction force is opposite the direction of motion. So the cosine of theta is the cosine of 180 degrees. Cosine of 180 degrees is -1. And so that would make whatever the work done is, I don't need to know its size, its number here, it would make it negative. So the work done by friction must be negative, must be less than 0. And so that allows me to answer question number 1. Question number 1 is that the work done by the normal force is 0, and the work done by the friction force is negative. So it's this guy here. So I hope that was okay. So let me go on to the second question, if I can. And this is a question about a brick that is dropped from a building, and it's a question about work done by gravity and gravitational potential energy. And in particular, are these quantities positive or negative? So let's just start with a little sketch here too, it'll be a simple sketch. So here's my falling brick. And here's its direction of motion. And it's falling under a influence of a gravitational force. And so here's the gravitational force. And so the question asks, what is the work done by gravity, and what is the change in gravitational potential energy? Well, for the work done by gravity, we can just use that equation again that relates the work done by a force to the force, the displacement, and the cosine of the direction between the vector force and the vector displacement. In this case, right, the motion, the displacement is downwards. In this case, the force is downwards. Gravity and displacement are in the same direction, so it's cosine of 0 degrees. So in this case, the work done by gravity, I don't need to know the number of joules, but it will be positive because displacement and force are in the same direction. What about the change in gravitational potential energy? Well, if you remember the change in gravitational potential energy, or the change in a potential energy, is the negative of the work done by the corresponding force. So that means that if the gravitational force does positive work, the gravitational potential energy gets decreased. If the gravitational force were to do negative work, the gravitational potential energy is increased. So if you lift a brick up, in that case, you're increasing the height of the brick. You're storing more gravitational potential energy. If you drop the brick is falling, then you're releasing gravitational potential energy. So in this case, the gravitational potential energy change is going to be negative, which is not what I've written. Is going to be less than 0. So that's the situation for that problem. We are unleashing or releasing gravitational potential energy, and that gravitational potential energy is actually going into the accumulating kinetic energy of the falling object. And so to answer that one, we want to look for work done by gravity being positive. That's the two middle ones. and gravitational potential energy changes negative. So I hope that was okay. Let me go on to the next one. Okay, question number 3 says a block slides down a frictionless incline from an initial height of 1 meter. That's block A. Identical block slides down a frictionless incline from a initial height of 4 meters. That's block B. And we've got to compare the velocities of the two blocks at the bottom of the incline. So let me just make a quick sketch of that. This is going to be a quick sketch too. We got one incline here. This is 1 meter vertical height. We got a second incline here. This is 4 meters vertical height. And our block is going to slide down, identical mass block is going to slide down these two inclines. So what happens from an energy perspective here? What happens is that the initial gravitational potential energy of the blocks at the top of the inclines get converted into kinetic energy at the bottom of the inclines. And so we're turning gravitational potential energy into kinetic energy. So let's compare how much gravitational potential energy gets turned into kinetic energy. Well, the initial height of block B, here's B, here's A, is 4 times higher. So B starts with 4 times the gravitational potential energy. At the bottom in the incline, then B has 4 times the kinetic energy. And then finally, kinetic energy is energy by virtue of motion. It depends on the speed. It depends on the square of the speed. Its relation to speed is the kinetic energy equals 1/2 mv squared. So to quadruple the kinetic energy, it must be that the speed is twice as big of B at the bottom of the incline. If the speed is twice as big, then the speed squared is 4 times as big, and then the kinetic energy is 4 times as big. And the kinetic energy was 4 times as big because the original elevation was 4 times as big, meaning the original gravitational potential energy was 4 times as big. So B has to be 4 times A. This little guy here. Okay. Let me go on to the next one if I can. So here we're told a block is dropped. In falling, we're asked questions about momentum conservation, about momentum conservation for the block, for the Earth, and for the block Earth system, the book Earth system. So again, let me make a little picture, and then we'll see in the picture the answer. Here's the book and the Earth. I've exaggerated it, obviously, hopefully. And let me add to this picture the momentum vectors that are acquired by the falling book and by the Earth due to the gravitational attraction between the Earth and the book. So importantly, the book is pulling the Earth down, but the Earth is pulling the book down, the block down, but the block is also pulling the Earth up, so that there are gravitational forces both on the block and on the Earth. The momentum of the block changes, And let's imagine some little time interval. It's acquired some momentum downwards. I'll call that the change in momentum, delta P, with a subscript B for block. And the Earth acquires a change in momentum. And I'll call that momentum, change in momentum delta P with a subscript E for the Earth. And these, importantly, these are vectors. They have sizes and directions. And if you were to watch these momentum vectors as the book is falling, the book's momentum vector will get larger and larger in the downwards direction. The Earth's momentum vector will get larger and larger in the upwards direction. The book's momentum is not conserved, it's growing. The Earth's momentum vector is not conserved, it's growing. But the sum of these two momentums, or the sum of the changes in momentum of the book and the Earth, that is staying the same. That is conserved. So if you look at the whole system, the total momentum of the whole system, the sum of the momentum of the book and the Earth, well, it started at 0 as the book was at rest in our hand. We dropped it. The sum remains 0. The individual momenta don't, but the sum remains 0. So that would be the momentum of the book-Earth system is conserved. So that's the answer to that one. Hope that's okay. On Canvas, it says the answer is 2 times for number 3. Oh, did I mark it wrong? I worked it out as 2 times. The velocity I worked out as 2 times. Did I put it down as 4? I've lost my notes now. The kinetic energy was 4 times. The velocity is 2 times. So if I marked 4 times, that was my mistake. I should have marked 2 times. Okay, so I'll go on to the next question. And that's question number 5. So we're asked to look at this picture here, where we have drawn the rotational motion of a rotating object. And we're asked some questions about the acceleration at the point A and the acceleration at the point B. And that's a matter of interpreting this, this graph of angular position versus time. So the key thing about these graphs is that the velocity if you want to see the velocity v, the angular velocity v, let me rewrite that. If you want to see the angular velocity v on an angle versus time graph, it's the slope. That's how to see it. So where it's steep, it's large velocity. Where it's shallow, it's small angular velocity. If you want to see the acceleration, the angular acceleration, that's the slope change. So if the slope is getting steeper or the slope is getting shallower, that corresponds to angular acceleration. And so let's look at these 2 points, right? Here, the slope is getting steeper. Just before point A, here's the slope. Just after point A, here's the slope. The slope has got steeper. B, the slope is not changing. Here's the slope before point B. Here's the slope after point B. It's the same slope. It's no steeper, no shallower. So there is acceleration here. And there's no acceleration here. Angular acceleration is positive here, and it's 0 here. And so if I'm going to answer this question, let me roll it up. The answer will be, let's see, at A, the object was accelerating. and B, the object wasn't accelerating, and so it's this guy here. Okay, question number 6. This one says you swing a ball in a vertical circle, and it's a question, you swing this ball on the end of a string in a vertical circle, and we've got to think about the centripetal force when we're doing that. We've got to think about the tension force when we're doing that, and we've got to compare the strength of the centripetal force and the tension force at the top and the bottom of the swing. So I'm going to need to draw a picture for this one for sure. So here's the vertical circle that the ball is swung in. And there's two interesting moments, when it's at the top and when it's at the bottom. And so we're going to think about those two moments. There are two forces that act on the ball, two individual forces. One is the weight, that's always present. And one is the tension force in the string. And those are going to combine to make a net force, which is the centripetal force. And so let's see if we can draw those forces. I'm actually going to draw the net force first. Normally, I'm normally drawing the individual forces first, but I think here it's a little easier to draw the net force or the total force first, and you'll see why. The key thing is that the ball on the string is moving around with constant velocity. And so that means that there's a constant in size centripetal force that's acting towards the center of the circle. So it always acts towards the center, and it has the same size because V is constant. So that's centripetal force, and that centripetal force is supplied by the sum of all the forces. So it is also the total force. And that total force is due to those two individual forces, tension and weight. So in the upper case, let me draw how the two individual forces add together. So I'm drawing the addition of two forces here. The second force I'm drawing on its tail on the tip, the head of the first force. The first one I'm going to imagine is the weight. That's downwards. It's always downwards. And the second one is the tension. It's along the string, which is downwards too. And so in this case, when the ball is at the top of the swing, those two forces are working together to provide the centripetal force. Downstairs here, it's different. Here's the weight, that's still downwards. But to create that centripetal force, it must be that there's a larger tension force acting upwards to counteract the weight and provide that centripetal force again. So what you see from the picture is some interesting stuff. And the answers to the question here, that the centripetal forces are the same at the top and the bottom because the speed is the same at the top and the bottom, but the tension force is smaller at the top. It's bigger at the bottom. It's because at the top, weight helps create the circular motion, but at the bottom, weight doesn't help. It acts opposite to what you need for circular motion. And so tension has to be larger. And so the centripetal forces are the same. That's response B and D. And the tension forces are different. So that's this guy here. Hope that was okay. So this one, I really think that one, if you make a good drawing, a good sketch, you just see the answer to the question in the sketch, in the drawing. If you don't make a drawing or a sketch, well, maybe you can just reason it out in your head, but I think the sketch drawing really helps. Okay, now we're on to question 7. And question 7 actually has several parts to it, really, that are questions 7, 8, 9, and I think 10. They all refer to this particular situation. So in this situation, we've got a 25 kilogram crate sliding down an incline, slides 0.8 meters down a 20-degree incline that is rough, i.e. has friction, and it slides with constant velocity, constant speed. And we're going to figure out the work done by various forces. The first work we're going to figure out how much work is done is the gravitational force. There's a really important point in this question that I had a few questions about this question, and the questions are normally, well, don't you need the coefficient of friction? And the answer is you don't need the coefficient of friction for this particular problem. The key thing is v is constant, speed is constant. That means that the sum of the forces, if you're not accelerating, the sum of the forces must be 0. And that fact is enough to determine the friction force. You don't need the coefficient of friction. So that's an important point here. Okay, so first of all, I'm going to draw all the forces. Actually, first of all, I'm going to just scroll down a little bit so I can see what work's done. I've got to actually calculate. I've got to do the work done by gravity, work done by normal, and I've got to do the work done by friction and the work done by the net force. Okay, so let's go back up, then I can do them all on here. So before I figure out the work's done, I'm going to just sketch the forces. And I think I'm going to write down also the magnitude of the forces, because I did calculate that. I got my notes here. Well, that doesn't make sense. Okay, so here's gravity, the weight. And since we know we got a 25 kilogram crate, then we can calculate the force of gravity by multiplying by acceleration of gravity. It's 245 newtons. So that's gravity. There's a normal force. Here's the normal force. Remember, it's going to be at right angles to the incline. And that normal force must be balancing a component of gravity, this one here, that is also at right angles to the incline. And so the normal force is actually, this is 20 degrees, this is 20 degrees. The normal force is the weight times cosine of 20 degrees. And so you can also calculate that number, and I did that. It was 230 newtons, I think. Okay, so that's two forces. Then we've got, in addition, a friction force. And so here's the friction force. It acts opposite the direction of motion. So it's sliding down the incline. And so that friction force is up the incline. And if, this goes back to this point, if the velocity is constant, if the sum of the forces is 0, this friction force must be balancing the other component of gravity. It must be equal to W sine 20 degrees. Only then will the forces parallel and perpendicular to the incline all cancel out. And I calculated that one too. It was 83.8 newtons. Okay, so those are my forces. And so now I'm in good shape. I can carry out the calculations of the work done by that master equation. The work done by force is the size of the force times the size of the displacement times the cosine of the angle between the directions of the force and the displacement. So let's do gravity. Let's do it first. In this case, we've got 245 newtons force strength. We've got a displacement of 0.8 meters. And it's the cosine of this angle here. That's the angle between the motion and the force. And that is 90 degrees less 20 degrees. So it's cosine of 70 degrees. And that came out to be 67 joules. Next one is the normal force. The work done by the normal force is, again, the same equation. We're going to put in the force strength. We're going to put in the displacement. They're not zero, but look, you're going to get cosine of 90 degrees. That's the angle between the normal force and the motion. And cosine of 90 degrees is zero. So that work done by normal force is zero. And then finally, the work done by friction force. That's the strength of the frictional force. That's 83.8 newtons. What happened there? I don't know, I want that to go away, but I don't know why it won't. I'll ignore it. Times the distance, times the cosine of the angle between the normal force and the motion. That's 180 degrees. That's this angle here. And so this will be 180 degrees. And if you calculate that, you get minus 67 joules. And so that's the work that is done by each of the individual forces. And then if you want there's a question in chat, I can see it. And I'll explain it after I get to the end here. I'll just do the net force. So the last part of the question asks, what is the net force done by all these individual forces? Well, you can certainly add them all up. And if you add them all up, you're going to get 0. 67 plus 0 plus minus 67, that will be 0. Or you could just say, well, look, if it's moving at constant velocity, its velocity is not changing, its kinetic energy is not changing, then by that, remember that work energy theorem? The work done by the net force is the change in kinetic energy. If the kinetic energy isn't changing, then there is no work done by the net force. So you can answer it that way too, without a calculation. So in chat, can you go over how you got the values of the angles for each calculation? Yeah, I can do that. First of all, so here's the 20 degrees. Let's make sure we're all in agreement that this angle in this triangle, that's also 20 degrees. The way I can see that is if I take this horizontal and rotate it by 90 degrees, I get, if I take the horizontal and rotate it by 90 degrees, I get this side. If I rotate this one by 90 degrees, I get the other side. And so this 20 degrees here is this 20 degrees here. The other way of seeing it, actually, I sort of like this way of seeing it. So that was a geometry way. You can turn these lines, these two lines for the incline, into these two lines for the force and its components by rotating them by 90 degrees. The other way you can see it is just imagine making the incline smaller and smaller, shallower and shallower. This is going to get smaller. And if you lower the block by lowering the incline, you see that that angle, you can picture that that angle would be smaller. So this is the 20 degrees that matches this 20 degrees. The adjacent side of this triangle, so W is the hypotenuse. The adjacent side is going to be W cosine theta. The opposite side of this triangle, let me erase this thing. The opposite side of the triangle is going to be W sine theta. And so it's the normal force is counteracting this guy. The friction force is counteracting this component. So the weight has two components, one parallel, one perpendicular to the incline, and the normal force and friction counteract those parallel and perpendicular components. I hope that makes sense. Okay, so these were in summary, these 4 results here are the answers to the 4 questions, 7, 8, 9, and 10. So let me head on down to question 11, that means. Here's question 11. It says a head-on collision between a 0.3 kilogram mass and a wall, and we're told that the 0.3 kilogram ball is approaching the wall at 2 meters per second and then bounces off the wall at 1 meters per second in the opposite direction. And we've got to calculate several things in this problem. One is the impulse given to the ball, one is the impulse given to the wall, and one is the changing kinetic energy of the ball. So let's do those 3 things. And I will start by making a sketch. So here's the wall, not a very vertical wall, is it? That's bothering me. I mean, it doesn't need to be a vertical wall, so I don't know why it is bothering me, but it did. And so we've got the ball that's heading towards the wall. So here comes the ball heading towards the wall, and here the velocity, I'll call it V initial, is plus 2 meters per second. And then it bounces off the wall, heads back in the opposite direction. And here the final speed, I call it VF, is minus 1 meter per second. And the signs indicate the directions and the numbers, the sizes here. Okay, so what's the impulse given to the ball by the wall? That means what is the change in momentum of the ball in the collision with the wall? So the change in momentum will be the final momentum minus the initial momentum. And that will be MVI, no, F, minus MVI. And we know all these numbers. The mass is 0.3 kilograms. The velocity change, let me pull the mass as a common factor out. Velocity change, what's that? Well, the final velocity is minus 1 meters per second. The initial velocity is 2 meters per second. I've got to subtract that. And so that's going to be minus 3. Minus 3 times 0.3 is going to be minus 0.9. I've run out of space. Let me clear some space. Well, let me just put it somewhere else. That's better. Minus 0.9 Newton seconds. So that's the change in momentum, or the impulse given to the ball. And it's negative because the ball was going in the positive direction and now it's going in the negative direction. So it's given an impulse in the negative direction. Now I'm going to just add a little b on that for the ball. What about the wall? What's the change in momentum of the wall? Well, the key thing here is that the walls in a collision, whatever, and two objects colliding, and here we're thinking the two colliding objects is the ball and the wall. If the ball acquires a certain change in momentum, a given impulse, then the other object, the wall here, must acquire an opposite signed or opposite directed but equal size change in momentum. And it's just like the, the forces of the ball on the wall and the wall on the ball are equal and opposite. The impulses given to the ball and the wall are equal and opposite. And so I don't need to do a calculation here. The wall's impulse is going to be plus 0.9 Newton seconds. And if you were to add these up, you'd get 0. That is, together, the ball and the wall are conserving momentum. And so that's an example of momentum conservation. That's question 11 and 12. Question 13 what is the change in kinetic energy? Delta Ke. That's the final kinetic energy less the initial kinetic energy. That's the way that we define it. And that will be, since kinetic energy is half mv squared, it will be half m, that's a common factor in the initial and final kinetic energies, times the difference between the squares of the initial and final velocities. And again, all of these numbers I know. So half times 0.3 kilograms times the final velocity squared, that's going to be 1, less the initial velocity squared, that's going to be 4. And this is going to come out to be, let's see, minus 0.45 joules. So the minus sign means that we lost energy in the collision, and you can see it, right? You can see the loss of kinetic energy of the ball in the collision because it's moving away slower than it approached. It approached faster. So it's lost kinetic energy. That's why the minus sign. And the amount depends on the change in speeds and the mass. It's 0.45 joules. And so that's the answer to those 3 questions that go with number 11. So this guy, and this guy here. Okay, hope that one was okay. Next one, clear. Okay, so here's a couple of questions about an astronaut. And we're told that an 70-kilogram astronaut standing on the surface of a newly discovered planet. We're told the radius of the planet, we're told the mass of the planet. We got to calculate the weight of the astronaut on the surface of the planet. This one's, and the next one, 14 and 15, are examples of universal law of gravity that we talked about in yesterday's class. I'm just finding my solution here. Okay. So for the gravitational force that's experienced by the astronaut, we're going to use the universal law of gravity, which says that the force is due to the masses, it's in proportion to the product of the masses, and depends on the square of the distance between the square of the separation between the masses. In this case, it's an important point here that, if we think about the astronaut on the Earth, maybe we, a little picture of them is here. Here's the astronaut on the newly discovered planet, sorry. Here's the astronaut, here's the newly discovered planet. The distance is the distance between the center of the planet and the astronaut. So that's the distance, it's the radius of the planet. And all of these numbers we know. I'm not going to write units here, but I really should write units, but I with writing with this pen is painful. So I'm going to fill in the gravitational constant. I'm going to fill in the mass of the astronaut. I'm going to fill in the mass of the newly discovered planet. And I'm going to fill in the radius of the newly discovered planet. Of course, I'm putting everything in SI units. So this is in meters. And if we calculate that force comes out to be 113 newtons. And so that was just a straightforward application of the a universal law of gravity that applies to any pairs of masses. Second part of the question says calculate the acceleration of gravity on the surface. Well, the acceleration of gravity on the surface of the Earth or the surface of the Moon or Saturn or this newly discovered planet, you can calculate the acceleration of gravity if you know the force of gravity and you know the mass of your object. And we know the force of gravity on the astronaut. We know the mass of the astronaut. All we got to do is divide this 113 Newton force by the astronaut's mass, 70 kilograms, and that comes out to be 1.6 meters per second squared. And so the force is the answer to 14. Acceleration of gravity is the answer to 15. And we did it with universal law of gravity. And also understanding, the relationship between gravitational force and gravitational acceleration, which is really Newton's second law. Okay, now we're on to the last problem. So this is a fully worked out problem where it's important that you would show all your working out to get all your partial credit. And as you know, I like drawing diagrams of forces. So we're asked to draw some diagrams in this and do some calculations. I need to go back to where the question was. Consider a 0.4 kilogram mass on a 1.4 long string. And we've got to compare it, compare the situation with the forces at the top and bottom of the swing. And we're told that at the bottom of the swing, the speed is 0.6 meters per second. And we're told that the swinging mass is 0.4 kilograms. So that's the information we're given. We've got the length of the string. We got the mass of the swinging object, and we got the speed of the swinging object. Those are the things we know. So this first part of the problem says, sketch the individual forces and the net force on the mass at the bottom of its swing and the top of its swing. So here's the, this one is the top. Of its swing. This one is the bottom of its swing. This is the highest point of the swing. This is the lowest point of the swing. And so let's add the forces in these two cases. So in this case, when we're at the bottom, there is a gravitational force downwards. I'll call that W. There is a tension force upwards due to the string. I'll call that T. And it must be, because the object is executing a circular motion here, it must be that there's a centripetal acceleration. It must be a centripetal force. And so if you add the weight and the tension together, and that's what I'm picturing here. Look, I drew the tension's tail on the head of the weight. The resulting force, the sum of the forces, that must be the centripetal force. I wrote that wrong. the sum of the force, I said it right, but I wrote it wrong. The sum of the forces, so this is sum of forces, equals the centripetal force. So that's a picture of the individual forces and the centripetal force and total force at the bottom of the swing. What about at the top of the swing? Let's see if we can do this one. Well, the weight will be the same. Weight doesn't change. The tension will be different though. The tension will, we don't know, need to know the details of how much different, but it will be in a different direction and actually a different size. But it is still along the length of the string. So here's my tension. And the key thing is that at this highest point of the swing, at the highest point of the swing, there is no centripetal force, because at that moment, the swinging object is momentarily stopped. It was going towards the left, it's going to go back to the right, it's momentarily stopped. So at that moment, there is no centripetal force. There's just a force that's going to be a tangential force that creates the tangential acceleration that is downwards along the circular path, tangent to the circular path that the ball is, or the object is going to fall back along. So here's the sum of the forces in this case. And that is not a centripetal force. That is a force that's going to create the tangential acceleration. And so those are the two pictures. And so I've done this one, and I've done this one. Okay, so then there's two calculations. Calculate the centripetal force at the bottom of the swing. So the centripetal force is given by this equation, which depends on the speed of the circular motion and the radius of the circular motion. I've written it down wrongly. I've got that. There's no r squared here. And so I just need to fill in that speed at the bottom of the swing and that radius of the swing, which is the length of the string that we were given in the problem. And those numbers, let's see, I wrote them down. It's 0.4 kilograms. Again, I'm going to be really lazy here. I would not do this if I was actually solving the problem to try and, if I was taking the test, I would put the units in, but because I'm using this this pen that I'm barely in control of, I'm not doing that. 0.4 kilograms times the speed, which was 0.6 meters per second squared, divided by the length of the string, the radius of the circular path, that's 1.4 meters. And if you calculate all that, that's 0.01 newtons. And so that's part C here. No, there's no. No 0.1, not 0.01. Okay, so that's good. Now we got to get the tension force. Well, let's consult our picture. The centripetal force, we said, was the net force, which is the sum of the individual forces. There was tension in the same direction as the centripetal force, and then there was weight in the opposite direction of the centripetal force. And so the centripetal force is the sum of the tension less the weight, this combination of these two forces. Now we want the tension. So if I rearrange that, the tension force is the centripetal force plus the weight. And so I can just add those together. The centripetal force was 0.1 Newton, and the weight here, the weight was, see, the mass was 0.4 kilograms. That means that the weight is 3.9 newtons. If I multiply by g, acceleration of gravity, and so that the tension force itself is 4.0 newtons. And so that's the answer to part D. And so that's working our way through the practice test.